All right, so in this video, we are going to do our second section of volume. In the last video, we went over how to find the volume using the disk method and the washer method. In this video, we are going to look at one new rule called volumes by cylindrical shells. So what this method is meant for is because in the real world, and in problems that we'll see, some volumes cannot be determined very easily using the previous methods. So what we can do is we can look at an alternate definition called the method of cylindrical shells. Now, on its surface, it does look a little complicated, but we're going to break it down a little bit for you. The volume formula for cylindrical shells is actually determined by 2 pi times the radius times the height times the rate of change, or delta R. So a way that you can break this down is that you can also think of this in this form right here, where 2 pi r is just the circumference of the circle that we're going to work with, that we're revolving around. Your h is the height of your function, and then delta r, or in our case dx, would just be the thickness of the shell that you're trying to form. Now, while I'm not going to make you know the exact geometric, all that stuff, it's kind of just breaking it down, here's essentially what the method of shells says. If we rotate around the y-axis, then the volume of the solid under the curve y equals f of x between a and b, where b is always bigger than a, would be the integral from a to b of 2 pi x times f of x. So a couple of things to note about the method of cylindrical shells. Number one, you notice that these are functions of x, but you are rotating around the y-axis. That is because you will have to work backwards with this method. So this technique is very helpful when you're trying to rotate around, let's say, the y-axis, but everything is written in terms of x's. So therefore, that is what's going to help you. All right. The other thing is that there is no squaring like there was in the disk and the washer method. Instead, to get your extra dimension that you're going to need, you would just multiply your function, or your radius in this case, by just a singular x. The 2 pi is your constant, so you could essentially factor that out front, and this would be 2 pi times the integral from a to b of x times f of x. That's the formula you would use when you're using the shell method around the y-axis. If you want to use the shell method rotated around the x-axis, you have to do everything in terms of y's. So whatever axis you rotate around, if you do the shell method, you have to use the opposite letter from the beginning. Everything else is essentially the same that we learned in the last section. Once again, though, no squaring. You're multiplying your function by a variable x, or if you're going the other way, it'd be a variable y. So at that case, we're just going to work some problems using the method of cylindrical shells here. So all the instructions today say the following. Use the method of cylindrical shells to find the volume of the solid attained by rotating the region bounded by the given curves. And the first one that we're going to do is y equals e to the negative x squared, bounded by y equals 0, x equals 0, and x equals 1. And I want you to rotate this around the y-axis. So we're going to take this black shaded region, and we're going to rotate it around the y-axis using the method of cylindrical shells. So if you have to go backwards from the y-axis, so our volume is actually going to be 2 pi times the integral from a to b of x f of x dx. And the important thing to note here is that since we're doing this in terms of x, even though you are rotating around the y-axis, you have to look at the x-axis to see if you need to do a washer method. And in this case, there is no washer method because there's no gap on the x-axis because we're doing x's. All right. So you can plug everything directly into this problem. So this would be 2 pi Now remember, this is in terms of x's, so you have to use your x-axis here. So we're going to go from 0 to 1 of x times your function, which is e to the negative x squared dx. To integrate this function, you will have to do u substitution. So u is equal to negative x squared, and du is equal to negative 2x dx, where du over negative 2x is your dx term. When you do u substitution of a definite integral, you need to make sure you change your parameters. So I'm going to come down here and do that. This would be 2 pi times the integral. Plug your 0 and your 1 into your u function. Plugging 0 in won't change anything, so you'll keep 0. But plugging 1 in and doing your order of operations will actually give you negative 1. So this would then give you x e to the u times your dx term, which is du over negative 2x. This allows us to cancel the x's off. And when you factor that negative 1/2 out to the front, you actually end up with a negative pi times the integral from 0 to negative 1 of e to the u du. Now you notice that your parameters are backwards. We can fix that by flipping it over and bringing an extra negative out front. So we can rewrite this as pi times the integral from negative 1 to 0 of e to the u du. Integrate e to the u doesn't change anything, so that will still be e to the u, and we're going to evaluate that from negative 1 to 0. So this will end up being pi times e to the 0 minus e to the negative 1, which gives us a final answer of pi times 1 minus e to the negative 1. You can distribute the pi through if you want to, but it's not necessary. That is the volume of that black shaded region around the y-axis using in terms of method of shells. As you can see, that was really necessary because the function was already written as y equals f of x, but we wanted to go around the y-axis. So instead of having to rewrite it like we did in the last video, we can go directly into the shells method and not have to worry about that. All right, let's look at another one. What if you're given the function y equals x to the 3/2 bounded by y equals 8 and x equals 0? That's going to give us this green shaded region. We want to rotate this around the x-axis using the method of cylindrical shells. So since we're going around the x-axis, the shell method says that we're going to do this in terms of y's. So it would be 2 pi times the integral from a to b of y f of y dy. So since we are doing this in terms of y, even though we are rotating around the x-axis, if you look at the y-axis here, there are no gaps. So that's going to be the dis method variation, which means you don't have to fix anything. We can go straight into setting this up, and it would be 2 pi times the integral. You must use your y-axis as your parameters, so that would go from 0 to 8 of y times your f of y function, which, it's not written in the right form. So what you will have to do back at the top is you will have to get this as x equals a function of y. So if I raise both sides to the 2/3 power, you can actually find that x is equal to y to the 2/3. So I would plug in y to the 2/3 as my function of y. All right, putting those y's together, I can write this as 2 pi times the integral from 0 to 8 of y to the 5/3 dy. Add 1 to the power and divide by the power. So that would be y to the 8/3 being multiplied by 3/8 evaluated from 0 to 8. I'm going to bring the 3/8 out front so that I can rewrite this as 6 pi over 8 multiplied by, this would be 8 to the 8 thirds minus 0 to the 8 thirds. Well, 6 pi over 8 simplifies into 3 pi over 4. 8 to the 8 thirds, let's see, the bottom number is your root. So the cube root of 8 would be 2. And then 2 to the 8th would end up being, let's see, 32, 64, 128, 256. So that's times 256. All right, so you can put this together. And let's see, 256 divided by 4 actually comes out pretty nice. That's going to actually just be 64. And then 3 times 64 makes that 192 pi. And that would be your volume using the method of cylindrical shells. Now, on one like that, you actually could have actually done the washer method and it would have worked out just fine. But if the instructions say use the method of shells on your test, then that's the technique I am grading you on. So even though it can be done a different way, I'm testing, do you know how to do shells? All right, so let's do another one. This time I've given you the parabola y equals negative x squared plus 6x minus 8, bounded by y equals 0, and I want you to rotate this green region right here around the y-axis. So using the method of cylindrical shells, and since you're going around the y-axis, we have to do x's. So this would be 2 pi times the integral from a to b of x times f of x dx, even though you are rotating around the y-axis, your region is around the x. So if you look at the x-axis down here, there are no gaps. So we can use the dis method variation, which means you don't have to adjust anything. You can go ahead and plug directly in your problem. This would be 2 pi times the integral. Since we're using x's, we're going to have to go from 2 to 4 of x times your f of x function, which was given to us as negative x squared plus 6x minus 8. Let's distribute that x through. So 2 pi times the integral from 2 to 4 of negative x cubed plus 6x squared minus 8x dx. So all of those are just anti-power rules. So go through and integrate each of those individually. So that would be 2 pi times negative x to the 4th over 4 plus 2x cubed minus 4x squared evaluated from 2 to 4. All right, so this would end up being 2 pi times. So go through and plug 4 into all of your formulas. So let's see, 4 to the 4th over 4 is the same thing as 4 cubed. So that's just negative 64. 4 cubed is 64 times 2 is 128. And then 4 squared times 4 is 4 cubed. So that's minus 64. Minus, and then go through and plug 2 into everything. 2 to the 4th is 16, and negative 16 over 4 is negative 4. 2 cubed is 8, and 8 times 2 is 16. 2 squared is 4, and 4 times negative 4 is negative 16. So after all of that, almost all of this stuff actually ends up canceling. So the 128 and the 2 negative 64s actually cancel. The 16s cancel. You have this negative of a negative 4, which is positive 4, times the 2 pi that's out front, and means you get a volume of 8 pi when using the method of cylindrical shells. So while it was a little bit ugly on the integration part, it actually canceled very nicely in the process. All right, so now we have to bring back the idea we saw in the last video where you have to also be able to rotate these regions around lines that aren't the axes. All right, so it's going to be a very similar technique to what we did. So let's look at this one. If you're given y equals 4x minus x squared, bounded by y equals 3, can you take that region and we want to rotate it around the line x equals 1 using the method of cylindrical shells? All right, so first off, the line you're rotating around is parallel to the y-axis. And since we're doing shells, we have to work backwards. So we would actually be doing that volume equals 2 pi times the integral from a to b of x times f of x dx. The problem is that you are rotating around a line that is to the left of the region that you're rotating. So remember last time, if you have a line that is below or to the left, you have to end up doing the function minus the line. All right. To the right and above is line minus a function. To the left and below is function minus a line. The difference is, though, in the shell method, you don't do this to f of x. This only affects the constant or the x variable that you're trying to multiply by. So when you set this up, this would become the volume equals 2 pi. So integrating from a to b. So using my two parameters here, that's going to be from 1 to 3. Instead of just being x, I have to take that x and subtract the line that I'm rotating around, which would be 1. And then you would multiply this by the function that you're applying to cylindrical shells, which would end up being 4x minus x squared. But this is not a dis method. Because once again, if you look at this shaded region, there is a big gap right here between what you're rotating around and the x-axis. So you have to do the washer method variation here. So your top function would be the 4x minus x squared, and then you have to subtract the inner function, which is y equals 3. So this is the outer function. This would be the inner function. And remember, you're not squaring anything because the part of shells, the x minus 1 in the front, that's taking care of the extra dimension that you need. All right, so now you've got to multiply all of this out. So this would be 2 pi times the integral from 1 to 3 and multiply all of this out. So it would be 4x squared minus x cubed minus 3x minus 4x plus x squared plus 3 dx. Putting your like terms together, let's see, there is a negative x cubed. You'll have a 5x squared. You'll have a negative 7x and a plus 3. Go through and integrate all those terms. That would be negative x to the 4th over 4 plus 5x cubed over 3 minus 7x squared over 2 plus 3x evaluated from 1 to 3. So this will be 2 pi times. So going through and plugging 3 into everything. 3 to the 4th is 81, so that would be negative 81 over 4. 3 cubed is 27. 27 divided by 3 is 9, and 9 times 5 is 45. Minus 3 squared is 9. 9 times 7 is 63, so that's going to be minus 63 halves. And then plus 9. Minus, go through and plug 1 into everything, which is a little bit easier. That'll be negative 1/4 plus 5/3 minus 7/2 plus 3. All right, so let's combine what we can. So you're going to have a negative 81/4 45 and 9 gives you 54, minus 63 over 2. Then you get a plus 1/4, a minus 5/3, a plus 7/2, and a minus 3. All right, combine your like terms. Negative 81/4 and 1/4 is negative 80 over 4, which is actually negative 20. 54 and 3 is going to be 51. Negative 63/2 and 7/2 is going to be negative 56 over 2, which is minus 28. And then you have the lonely minus 5/3. So this is 2 pi times negative 20 plus 51 is 31, and 31 minus 28 is 3. I need to subtract 5/3 from that. So let's see, that would be 15/3. Sorry, that'd be 9/3. 9/3 minus 5/3 is 4/3. And then multiplying it by 2 pi as far as your shell goes, your final volume here would be 8 pi over 3. So that one is a little bit different on two regards. Number one, you had to rotate around a line that was to the left of the shaded region. So that adjusted my shell part. And then since it is a gap between the shaded region and the x-axis, you had to do the washer method variation and therefore do your outer function minus your inner function. So a couple of variations there, but the overall, same exact idea. So let's do one more just like that, because that one, last one was a little bit longer, a little bit different. So let's do one very similar. It says, once again, use the method of shells, and we've got y equals the square root of x and y equals x cubed that we want to rotate around the line y equals -1. So y equals -1 is parallel to the x-axis. And since we're doing shells, you have to go backwards. So therefore, we're going to end up doing volume equals 2 pi times the integral from a to b of y f of y dy. Now you got a few things to deal with here. So number one, you are rotating around a line that is below the region that we just found. That's the exact same thing we just did. When your line's below the region that you're rotating around, you have to do the function minus the line. So that's going to affect that part. So that part's going to end up changing. And then also your f of y. Since there is a gap to the y-axis of the region, you have to do the washer method variation. But I need both of these functions to be in terms of y, which they are not. The original problem, you're going to have to solve both of those functions for x in order to do this. So if you solve for x in the first one, that would be y squared. And on the second one, that would be the cube root of y. So when you apply both variations to your shells method, volume is going to equal 2 pi times the integral. So you're doing your y-axis, so that would be from 0 to 1. That's probably the best part of this problem. It would not be y in this case. You would have to do your function, which is y, minus the line you're rotating around. So y minus a -1 is y plus 1. And then your f of y, like I said, there's a gap right here. So you have to do your washer method variation, which means you have to do your outside function, which is the blue graph. Now the blue graph is traditionally the x cubed graph. So we would have to call that the cube root of y. Now the cube root of y can be rewritten as y to the 1/3 minus your inner function, which is the square root graph. But after we converted it, it became y squared. And after all the manipulation and everything, this is what you end up with. So we adjusted the shell part and we adjusted for the washer method technique. You need to FOIL this. So this will be 2 pi times the integral from 0 to 1. So let's see, foiling this would give us y to the 4/3 minus y cubed plus y to the 1/3 minus y squared in terms of y. All right, none of those combined, so we're going to have to go straight into our integration. So integrating all of those would give us y to the 7/3 being multiplied by 3/7 minus y to the 4th over 4 plus y to the 4/3 being multiplied by 3/4 minus a y cubed over 3 evaluated from 0 to 1. And the best part of this, even though those are a lot of ugly integration terms, only number you have to plug in is the 1, because plugging 0 in will make all of those go away. So this would be 3/7 minus 1/4 plus 3/4 minus 1/3 when I plug 1 in. Once again, no need to plug 0 in because at the end it's going to all end up going away. You can put your 2/4 terms together. So this would be 2 pi times 3/7. Negative 1/4 plus 3/4 is 2/4, which is just a half. And you're going to subtract a third. We need to find common denominators. So 7, 2, and 3. The common denominator there would be 42. So if I convert all of those fractions to have a denominator of 42, you should get 18 over 42, 21 over 42, and what is that? Times 10 times 4, so minus 14 over 42. So that would be 2 pi times 18 and 21 is 39, and 39 minus 14 is 25 over 42. Well, the 2 and the 42 both share a 2 in common, so that 2 cancels. That becomes a 21, and your final answer would be 25 pi over 21 as the volume using the method of cylindrical shells. So that's another example where you have to adjust your shell part because you're rotating around y equals -1, and you also had to use the washer method because of the gap between the y-axis and the graph that you were rotating. That ends section 6.3. So that ends the third different technique of volume. In the next video, we will be doing something a little bit different, so no more volume. We will move into the idea of an average value function, which has something to do with the mean value theorem that you did in Calculus 1.